Usually when we think about building like serious athletic power, there's this expectation of just massive grinding physical exertion.
Oh, absolutely. The classic no pain, no gain mindset.
Right. If you want a bigger, stronger athlete, you bring in the heavy iron. You
Yeah.
load up that barbell until the steel is literally bending across their shoulders, and, they just have to fight gravity.
Yeah, we really do have this very Newtonian expectation of the body. Like heavy mass applied to the muscles forces them to adapt and get stronger.
Exactly.
And I mean, that's the traditional model of mechanical tension. For
Hmm.
decades, the standard wisdom has been that you need to lift something incredibly heavy,
Huh.
usually 70% or more of your absolute maximum capability,
Mhm.
just to create those microscopic tears in the muscle tissue that actually trigger serious growth.
But then you step into the world of youth athletics, right? Specifically adolescent development, and suddenly that heavy steel approach is, well, it's a massive liability.
Oh, for sure. It completely changes the math.
Yeah, because we're looking at a developmental landscape where applying heavy, high-load weights to, growing joints, open growth plates, developing skeletal structures, it's just incredibly risky.
It is.
You want these young athletes to get the hormonal and strength benefits of a heavy squat, but their knees and their spines really shouldn't be grinding under maximum loads, especially if a coach can't watch their form every single second of the workout.
Right, which creates this really profound dilemma in sports science. How do you stimulate the explosive strength and the muscle mass required for elite athletic performance in adolescence, but, without subjecting their fragile musculoskeletal systems to those dangerous heavy loads?
And that is exactly the problem we are tackling today on this deep dive. We are exploring a fascinating, highly practical solution that was laid out in a 2026 randomized controlled trial.
It's a great paper.
It really is. So, this study was published in the Journal of Sports Science and Medicine by a team of researchers led by Liang Qing and Tianyu Zhao. The title is a bit of a mouthful, but it's called Effects of Blood Flow Restriction Training at Different Levels of Arterial Occlusion Pressure on Body Composition and Athletic Performance in Youth Soccer Players.
Quite the title.
Yeah, academics love a long title. But what they are actually testing is basically the biological magic of using incredibly light weights paired with pressure cuffs.
Right. This approach is called blood flow restriction training, or BFRT. And the core concept here, it basically flips the traditional lifting model upside down.
How so?
Well, instead of 70 or 80% of a one-rep max, these athletes are using just 30%.
Wow.
Yeah, a weight so light it honestly barely feels like a warm-up.
Oh.
But by applying localized pressure to the limbs during the exercise, BFRT creates this unique intramuscular environment that essentially tricks the body into growing as if it were lifting maximal weight.
I love that. Hacking the body. So the mission for our deep dive today is to explore exactly how this BFRT mechanism, hacks those growth signals. And more specifically, we're going to look at how King, Zhao, and their team hunted for the Goldilocks zone of pressure.
Yes, the 40 versus 60% question.
Exactly. They pitted 40% arterial occlusion pressure against 60% to see which specific squeeze actually yields the best real-world on-field athletic performance.
To really appreciate the nuance of that 40 versus 60% pressure, you really have to grasp what is happening at the cellular level when those cuffs inflate.
Okay, lay it on us.
So the researchers used these tourniquet-style cuffs, and they applied them to the proximal portion of the lower limbs, so the very top of the guys.
Right.
But the goal isn't to cut off circulation completely. The cuff is inflated to a precise pressure that partially restricts arterial inflow while markedly limiting venous outflow.
Okay, I was trying to picture this fluid dynamic earlier, and it makes me think of kinking a garden hose.
Oh, that's a good analogy.
Right, so you kink the hose just enough that the water from the spigot is still spraying into the tube, but you block the drain on the other end, so the water is just pooling and swelling and building up this massive pressure inside the hose.
That's exactly it. The human vascular system responds in a very similar way. The arterial blood, which carries the oxygen, is still pushing its way into the working leg muscles because arterial pressure is naturally quite high.
It forces its way past the cuff.
Right. But the veins, which operate at a much lower pressure to carry blood back to the heart, they are effectively pinched shut by the cuff.
So it's a one-way street. The blood just pools in the legs.
Yep. And when an athlete starts performing squats with this pooling happening, You create a localized ischemic and hypoxic environment inside the muscle.
Okay, let's break those terms down for the listeners. Ischemic meaning a restricted overall blood supply, and hypoxic meaning the environment is starved of fresh oxygen, right?
Spot on. The muscles are contracting, they're burning through their available ATP, their cellular energy, and they desperately need fresh oxygen to continue operating efficiently.
But because of the cuffs, that fresh oxygen just isn't arriving.
Exactly. And because the muscle is working in this hypoxic state, there is a rapid accumulation of metabolic byproducts. We're talking primarily about lactate and hydrogen ions, and they simply cannot be flushed away.
So this localized pooling of acid, it basically sends a panic signal to the central nervous system, doesn't it?
It absolutely does.
Uh-huh.
The brain senses this massive accumulation of lactate and this extreme low oxygen environment in the legs, and it assumes the body is under extreme duress. It's thinking, we are failing, I need to call in the big guns immediately.
The big guns being your high threshold, fast twitch, type 2 muscle fibers.
You got it. Human physiology follows a very strict recruitment order. Normally, your body is incredibly efficient, almost lazy, really.
Yeah, it doesn't want to work harder than it has to.
Right. It relies on your smaller, oxygen-loving, type I slow-twitch fibers for as long as possible, just because they don't fatigue easily. It keeps those explosive type 2 fibers in reserve for absolute emergencies.
Like lifting a wildly heavy weight or, I don't know, sprinting away from a bear.
Exactly.
But doing a squat with 30% of your max, that shouldn't require type 2 fibers at all, normally.
No, under normal conditions, your type I fibers would handle that light load all day long. But under blood flow restriction, those type I fibers suffocate.
Oh, wow.
Yeah, they rely on oxygen, and you've cut off the supply, so they fatigue almost instantly. And the brain, desperate to keep moving the weight, is forced to preferentially recruit those high-threshold, fast-twitch type 2 fibers.
Even though the physical weight on the barbell is practically nothing.
Exactly. It's a physiological trick.
So bringing this back to the U16 soccer players at the China football school who actually participated in this trial, you have these young adolescents whose joints are still, pretty vulnerable. By using this BFRT protocol, they are getting the intense muscle fiber recruitment, the localized metabolic stress, and that subsequent hormonal cascade of a heavy lifting session.
Yep.
But their developing knees and hips and spines are only bearing 30% of the load.
It is a profound paradigm shift for long-term athletic development. I mean, you completely eliminate the cumulative mechanical wear and tear on developing cartilage and bones, but you're still maximizing the muscular adaptations.
Okay, but wait. If the whole point is to trap all this lactate and starve the muscle of oxygen so the brain hits the panic button, why are we stopping at 60% pressure?
What do you mean?
Well, if I'm an athlete trying to get massive legs and maximum power, my instinct is to just crank those cuffs up to 80 or 100% to absolutely maximize that metabolic stress. Like, more is better.
Yeah,
for you.
it definitely seems intuitive that more restriction would equal more adaptation. But biological systems rarely operate on a straight infinite line. It comes down to a concept known in biology as the hormesis hypothesis.
Hormesis.
Right. Hormesis describes a dose-response curve where a moderate amount of a stressor triggers a highly beneficial adaptation. But pushing that stressor too high becomes toxic or just counterproductive.
Oh, like exposure to sunlight. A little bit gives you vitamin D, too much gives you radiation burns.
Exactly the same principle. When you push occlusion pressures to 80% or 100%, you start to overly restrict that arterial inflow.
So you're blocking the water from entering the hose completely.
Yes. And the tissue becomes so ischemic that you actually alter the motor unit recruitment patterns in a negative way. The muscle simply cannot function. And, furthermore, pressures that high drastically increase subjective discomfort.
Meaning it hurts.
It crosses the line from the normal burn of a hard workout into outright agonizing pain.
Which completely destroys long-term training adherence. I mean, no 16-year-old soccer player is going to enthusiastically strap the cuffs back on for week 2 if week 1 left them in excruciating pain.
Adherence is the foundation of any athletic program. So the researchers' goal in comparing 40% and 60% was to map that hormesis curve. They were looking for the perfect middle ground between physiological efficacy and psychological tolerability.
Let's look at how they actually set up the map for this. They took 24 male U16 soccer players and split them evenly into 3 groups.
Right, 8 kids per group.
Yeah. A 40% arterial occlusion pressure group, a 60% group, and a control group that just lifted the 30% load normally with no cuffs at all. They train 3 times a week for 6 weeks, doing a lower limb routine of back squats, deadlifts, and loaded lunges.
And the strictness of the protocol is really worth noting here. They use these wireless automated cuffs called air bands.
Very high tech.
Very. The pressure wasn't just some random squeeze. The bands individualized the pressure based on each athlete's specific thigh circumference.
Oh, that makes sense.
Yeah, because the thigh circumference is the strongest independent predictor of how much external pressure is needed to actually occlude the artery through the fat and muscle tissue.
Oh, right. And the rep scheme they put these kids through, it honestly sounds brutal when you consider the cuffs stay inflated the entire time.
It's not easy, that's for sure.
They did 4 sets per exercise, 30 reps for the first set, followed by 3 sets of 15 reps, with only a 60-second rest between sets. And the cuffs inflate at the start of set 1 and don't deflate until the very end of set 4.
Yeah, that is roughly 12 to 15 minutes of continuous unbroken occlusion and metabolic pooling per exercise block. It maximizes the time the muscle spends in that hypoxic acidic environment.
So these kids spend 6 weeks with cuffs squeezing their legs. Does that extra 20% of pressure in the 60% group actually force the kind of extreme adaptation the researchers hypothesized?
The physical changes were incredibly stark.
Yeah.
Yeah. Over the 6 weeks, overall body fat percentage didn't change across any of the groups, which, is entirely typical for adolescents going through a predominantly anabolic rapid growth phase.
Sure, they're teenagers. They're just eating and growing.
Right. But the lower limb muscle mass, the actual cross-sectional size of their legs, saw massive divergence. The control group saw almost zero change from lifting the light weights alone.
Because 30% without cuffs is just a warm-up.
Exactly.
Mm.
Now, the 40% AOP group gained an average of 0.55 kilograms of leg muscle.
Which is pretty solid for 6 weeks.
It is. But the 60% AOP group completely blew past them.
Only guess.
They gained an average of 0.83 kilograms of leg muscle.
Wow. That is nearly 2 pounds of pure muscle tissue added to their lower bodies in just a month and a half, using weights that are basically equivalent to an empty barbell.
It's incredible. And that new muscle tissue translated directly to raw force production. When they tested the athlete's maximal back squat, their 1-rep max, both BFRT groups, got significantly stronger.
Okay, hit me with the numbers.
The 40% group added an average of 6.50 kilograms to their max. But the 60% group added a massive 9.25 kilograms to their max squat.
Okay, so how does a tighter cuff squeeze out an extra half pound of muscle tissue and an extra 3 kilos of squat strength? Biologically, what is happening at 60% that isn't happening at 40?
The tighter restriction at 60% amplifies 2 very specific intracellular pathways. First, you have greater cell swelling.
Cell swelling, okay.
Yeah, because the blood is pooling so intensely, fluid is driven from the bloodstream directly into the muscle cells themselves. The cells literally gorge with fluid, expanding like little water balloons.
Ouch.
Well, this severe physical stretching of the cell membrane is detected by mechanosensors, which basically interpret the swelling as a threat to the cell's structural integrity.
So the cell responds by aggressively upregulating protein synthesis to reinforce its walls.
Precisely.
It builds more muscle just to survive the fluid pressure.
It's an adaptation to stress.
Hmm.
And the second pathway involves reactive oxygen species, or ROS.
I've heard of those, usually in a negative context, right?
Usually, yes. In a hypoxic environment, mitochondria become stressed and leak these highly reactive oxygen molecules. Now, while chronic ROS is bad and causes oxidative stress, acute spikes of ROS act like a chemical flare gun inside the muscle.
A flare gun?
Yeah. The flare goes up, and it signals a massive localized release of growth hormone and insulin-like growth factor.
Oh, wow.
And the 60% pressure seems to push both the cell swelling and those ROS flare guns to their absolute maximum effective limit without crossing over into the nerve damage or motor unit shutdown we see at 80%.
So if you want pure raw size and a massive back squat, 60% pressure is the undisputed king.
Undisputed.
But here's the pivot, right? These guys are not competitive powerlifters. They are soccer players. So the million-dollar question for anyone listening is whether that bigger engine actually translates to better handling on the field.
Right. Because muscle mass doesn't matter if you can't use it in a game. The researchers tested 2 highly relevant field metrics. They tested explosive vertical power using a counter movement jump, and they tested multi-directional agility using a t-test.
The t-test is where the athletes have to sprint forward, shuffle side to side, and backpedal around cones as fast as possible, right?
Exactly. It's a great measure of agility.
And this is where the data completely breaks from the raw strength results. We know the 60% group has significantly more leg muscle and significantly stronger squats.
Right.
But on the jump test and the agility test, both the 40% and 60% groups improved equally. The 60% group had zero additional benefit.
It's fascinating.
They had a bigger engine, but they weren't jumping higher or changing directions faster than the guys with the smaller engine. Why is that?
This phenomenon highlights a really vital concept in sports science known as the stretch shortening cycle. Jumping and rapid agility are not just about raw muscular contraction. They rely heavily on your tendons acting like coiled springs. When you dip down before a jump, you rapidly stretch the Achilles and the patellar tendons. They store elastic energy, and then the nervous system has to fire perfectly to release that energy in a fraction of a second.
So it requires a highly efficient neuromuscular transmission system to actually utilize the raw strength.
Yes, and that transmission system has a ceiling. The 40% pressure was entirely sufficient to stimulate the neuromuscular coordination and the stretch shortening cycle efficiency needed for those movements.
So building a bigger muscle at 60% didn't improve the tendon elasticity or the neurological firing sequence any further.
No, they simply plateaued.
Which introduces a massive practical consideration for coaches. The researchers tracked perceived exertion using the Borg scale, which is basically a subjective rating of how hard and painful the workout felt.
Right, from 0 to 10.
The 60% group reported a 5.3 out of 10. The 40% group reported a 4.2.
And that matters. If the 40% pressure delivers the exact same improvements in jumping and agility on the soccer pitch, but it requires significantly less pain and discomfort, well, it becomes the vastly superior tool for a strength coach.
Because you keep your athletes' morale high. You guarantee they show up for the next session without dread, and you still secure the field performance boosts that actually win games.
Exactly. It's about optimizing the whole training environment, not just the muscle.
But the data throws one final curveball at us.
The sprints.
The sprints. We have athletes with thicker muscles, stronger squats, higher vertical leaps, and faster multi-directional agility. But when the researchers timed their straight-line 30-meter sprints, nobody got faster.
Not a single group.
Not the 40% group, not the 60% group. Zero improvement across the board. If they have more fast-twitch muscle fibers, which are literally designed for sprinting, why aren't they faster?
It reveals the hyperspecificity of the human nervous system. Sprinting, particularly early acceleration and top-end linear speed, requires the nervous system to fire motor units at astonishingly high velocities. We are talking milliseconds.
And BFRT recruits those fast-twitch fibers, but it recruits them through a slow, grinding metabolic panic. It's a localized chemical stimulus happening while the athlete is doing slow reps of loaded lunges.
That's the key right there. The metabolic stress updates the muscular hardware, it builds the cross-sectional area and the pure force capacity.
But the nervous system is the software.
Yes. And BFRT lacks the instantaneous high-velocity neural stimulus required to rewrite the sprinting software. You can give a computer a faster processor, but if the operating system doesn't know how to run the new speeds, nothing changes.
So to actually drop their 30-meter sprint times, an athlete would have to take that newly acquired muscle mass from the BFRT and train it with dedicated, unrestricted speed work.
Right. Things like plyometrics, drop jumps, or resisted sprints, where the central nervous system is forced to practice high-velocity firing rates. You cannot just build a tissue and expect the brain to magically know how to orchestrate a perfect sprint.
The structural capacity increases with BFRT, but the specific skill of sprinting still requires specific practice.
Exactly.
Well, stepping back to look at the entire landscape of this study, low-load blood flow restriction training proves to be an incredibly potent tool for youth development. By using just 30% of an athlete's max weight and applying targeted occlusion, coaches can completely bypass the joint-crushing mechanical tension of heavy weights and rely on cellular swelling and metabolic stress to force massive gains.
And the application of those gains depends entirely on the chosen pressure. I mean, for pure hypertrophy, rehabilitating atrophy, or maximizing pure squat strength, 60% arterial occlusion pressure is unmatched. The heightened ischemia drives phenomenal tissue growth.
But for coaches looking to boost practical field skills like jump height and multi-directional agility, a moderate 40% occlusion is equally effective, and it spares the athletes a significant amount of discomfort. Though regardless of the pressure, athletes still need to dedicate time to high-velocity neural training if they want that raw power to translate into top-end sprint speed.
The methodology these researchers employed is brilliant, especially their load velocity profiling methods to predict maximum strength safely without actually making the kids lift a true 1 rep max.
Right.
I highly encourage you to dive into the full methodology. The article is by King et al., published in the Journal of Sports Science and Medicine, and it is a fascinating blueprint for modern athletic development.
It is definitely worth tracking down and reading in full. And, if you want to ensure you never miss another deep dive into the latest sports science, human biology, and performance research, make sure you follow the channel and turn on notifications.
And I'll leave you with a final concept to mull over. We've spent this time discussing how BFRT protects the fragile joints of developing teenagers while tricking the nervous system into adapting.
Right.
Imagine taking this localized high metabolic stress protocol and applying it to an athlete recovering from a catastrophic structural injury, like an ACL tear or an Achilles rupture,
Oh, wow.
right? Could this low-load environment be the key to injury rehabilitation, allowing a recovering athlete to maintain elite, fast-twitch muscle strength without risking any dangerous mechanical tension on their newly reconstructed tissues?
The idea that we could halt muscle atrophy during rehab without loading the joint, it's incredible. It could completely rewrite the timeline for returning to sport. Something to think about. We will catch you on the next deep dive.